Previous to that, I spent the last 18 years at Seabird Scientific and from wet labs, working in various different roles there. But decided it was a good chance for a change and come back into academia and do a little more teaching, a little more lecturing, a little more mentoring, and a lot more research. I got my background with my postdoc with Colin Ressler while she was at Bigelow. Spent a lot of years with Emmanuel Boss and Ron Zanafeld's lab, and ended up actually getting my PhD from Oregon State at the same time, and also did my master's where I first met Colin as well back in the early 1990s. So that's been on my history. I will tell you the other thing is that was mentioned already this morning. I'm not a physicist. I'm a biological oceanographer that's kind of become an experimentalist. And that's a good thing for me as it turned out in the long run, because I got a lot of work with a lot of instrumentation, getting them out in the field, making the measurements. And for me, that was how I learned more about the theory, what we're going to talk about in this class. Just getting my hands on data and the instruments was my best way to do some interpretation of complex things you're going to see about like radiative transfer. So everybody's going to have their own different learning style is my encouragement here. Some of you are more physics minded, some of you are more mathematically minded, some of you are going to be more biologically minded, experimentalists. Just make those connections and don't ever hesitate to reach out to people for help. So I'm happy to give the first, oh, I've done it now. I think I must have lost it from here.
We're on Zoom.
Yeah. Okay. So I'm trying to give you a little bit more background on what this course is about, which I think it's about. Of course, I'm taking it before. So I wanted to start out with a little bit of a thought experiment. I'm hoping you guys will think a lot about this over the next couple of weeks. So this is a painting done by Ron Zanefeld called Light in the Sea, Man in Nature. It's painted in 1998. So this is really the underwater view of the ocean environment, at least in terms of the surface waters. I've always loved this painting because every time I look at it, I start to see more and more facets in this painting that are amazing that have been captured here. So I wanted to start out with you guys today, just asking some good questions. It's going to be for you to think about as you go through this course. What do you see in this painting? Why is the water blue? Why does the intensity of light change with depth? What's the cause of that circular pattern that's right up there against that sampling platform, which is loaded with a whole bunch of optics instruments on it? Why do you see the light and dark patterns in the water and on that shark that's there? But more importantly, what don't you see in this picture? So keep thinking about those questions as we go through the next 2 to 3 weeks here. Because again, every time I came back to this, it was really amazing to see that how much of that underwater light field is captured in this painting. So now I'm going to step up to the Earth orbit here and what a satellite sees. So this is a picture from an aquamotus color image from 2017 off Africa's Benguela upwelling ecosystem area. So it's sort of the same view now, or same set of questions. What do you see in this image? Why does the intensity of light change throughout this image? You see some brighter areas, you see some darker areas. What's the cause of that? What do you not see in this image? So think about that. There's a lot of answers to each one of these, but I really want you to understand that from the satellite perspective, the only thing the satellite is measuring is light. Solar light that comes in gets reflected or put into the ocean, comes back out of the ocean or off the atmosphere. That's the only thing this is. The satellite is measuring the ocean color imager. It's measuring its light. So what is ocean color? What is the color of the ocean? Well, we just saw a bunch of images, or an image, a satellite image from Otis. I put this in here. It's on the NASA website. I think it's the PACE website. I can't remember for sure, but it is, because this is all about what the next OCI imager is that's going to be launched by NASA. But the important point is that most of the time when we've done ocean color imaging, we're only doing it at a few spectral bands across the visible region. The PACE mission, the OCI instrument, will actually do a full, more continuous spectrum of readings, which is really important for trying to understand much more about the ecosystem, surface ecosystem. The ocean color, I have to stand around. Sunlight passes through the earth. So what's on the bottom here? Sorry, let me go over here. Sunlight, the bottom picture is basically just showing that ray tracing.
I'm gonna remove the other mic.
Sunlight comes down through the Earth's atmosphere, it interacts with that through the process of absorption and scattering that stuff that's actually in Earth's atmosphere, which is clouds, water vapor, aerosols. Some of that gets all the way to the surface, air-water surface. Some of it's just directly reflected out off the surface of the ocean. Some of it gets into the water, undergoes again that same fate, going and interacting with the constituents of the ocean, going through an absorption or scattering process if they're colored material that that's in the ocean. Lots of stuff in the ocean. There's very clear waters, not a whole lot of constituents in the ocean, ranging up to very phytoplankton-rich waters, suspended sediments in the water. Each of those gives a different spectral view, constituents, a spectral view off the ocean. That's what's creating the color. Just remind you too, there's two fates of a photon in the ocean or in the atmosphere: scattering or absorption. So this course, I think, I love this picture Colin created, is really going to take us through this journey, back and forth journey. I started at the view, at the view of the underwater light view. I showed you the satellite. So what we're going to do is work from up and down this tree here over the next, or series of balls over the next week or so. Satellite, going into the radiometry, the inherent optical properties, measuring and the absorption, scattering in the ocean, trying to connect that to the actual constituents we really want to know about. Phytoplankton cells are there, how tight they are, the particular organic carbon, then trying to get to the ecosystem, carbon cycle, climate system, these bigger questions about the health of the ocean. So this week, we're going to start really at the inherent optical properties, to move up and down a little bit and change on this. Week 2, we'll go much more into the radiometry and then a little bit more into the remote sensing part in those discussions. We'll dive a little bit more into week 3 into the remote sensing, the reflecting submersion methods, how do you get to give you the answers about the IOPs, and the oceans, and also cover some more optical measurements, data processing, atmosphere corrections, and in week 4. It's really the census week, working up the field data collected in week 3, and having a lot of presentations, and hopefully at the end having a big part. So goal here, next goal is just to give you some real basic terminology on radiometry. Again, as I just mentioned, next week we'll go over a lot more detailed aspects of what radiometry is, the AOPs, all these discussions more to have you understand more about the radiometric processes. So radiometry is the science of measuring the electromagnetic radiation. In ocean optics, optical radiometry most often refers to just the visible, or UV visible, near infrared regions, what your eyes can see, the boundary condition there. However, you'll see in satellites, oftentimes there's measurements being made out to the sphere and areas really that look much more about what's in the atmosphere components. So some basic radiometric quantities here. Look to the center here of this box. First, we start out with radiant energy. The symbol typically used is Q. That's the unit of measurement in the joule. We take that radiant energy. Now we try to quantize it in terms of time. So it's the time, which gives us a watt. That's typically shown as phi, and we call it either radiant flux. More often you might see it. Then we take that radiant flux, and now we want to measure it on a surface. That's irradiant. And the pictogram here in the center box is, and in the upper diagram here in the upper right-hand corner, is basically saying I have a predicted area, a surface area, where I'm going to try to see how much light's hitting from all different angles. Finally, there's radiance, which is really truly the basis of the radiative transfer equation, which you'll know more about soon. And that is then trying to quantize it in terms of how much radiant flux or power is per solid angle per unit projected source area. Now we're looking at a little sphere. On that sphere, as we're centering and looking at it, we're just looking at some little tiny section of the spheres. The other thing to note here is that all of these quantities I just measured, just talked about, are always per nanometer. So how do you do that? Well, the per nanometer means it can be something like par, where it's over a huge number of wavelengths, or it can be quantized in terms of like every 10 nanometers I'm going to do that. But you always have to normalize that per nanometer. There's some other properties I just highlighted there, which are typically called apparent optical properties. We'll discuss these more, but these are more like relationships. The middle one I'm going to point out to, that's used in satellite oceanography called remote sensing reflectance, which is basically how much light is coming out of the ocean relative to how much light is coming out of the ocean. So it's a normalization. So it's upwelled radiance divided by downwelling irradiance. Mobley has a really good description to this. It sort of connects all the dots. If you remember, I just talked about radiant energy. That's on the far right-hand side. If you take it and then try to look at that radiant energy flowing in, it becomes radiant power. From that, you can calculate the power per unit area. From surface area, now we're going to look at how much of that radiant power is moving. So that's irradiance. You can also just look at intensity, and that's the radiant power solid angle. And if you take the area radiant energy or radiant power per unit energy, or sorry, per unit surface area and per unit solid angle, that's radiance. The other thing I liked about this is that it really depends on the view of making study of observation. So each one of these little boxes I just talked about, radiance, irradiance, you can do from onto a surface. That's typically what we think about, projecting some light onto a surface. That's the irradiance, but you can also look at it from the standpoint of how much is being emitted from the surface. That's going to come important too, because as we start talking about some other sensors that are active light, so we're seeing light. So each one of these has that perspective onto a surface, from a surface. So it's good to keep that in mind. And they do have different definitions. You see them different literature. All right, so this is an interesting area too. So why do we love looking at ocean colors? How our little color maps all come out. NASA and European Space Agencies have done these color palettes. because they want to put them into a photopic kind of point of view. What do I mean by photopic? Photometry is really the special subset of radiometry that's weighted for what we see by the human eye. So that's where, coming back all the way to the perspective, what is ocean color? We're trying to equate it again, put it in perspective what our eyes can see. So, other thing I just wanted to point out too is that there is a photopic response or a weighting function for the human eye based on the colors of red, and some other rods we have in our eyeballs. But there's a lot of other organisms in the ocean which have very different photopic response. Some of them we see in multicolored bands. Some of them see only polarized or unpolarized light. So there are many, many views going back to that painting that all those creatures are seeing in that same light. Finally, this is from an old sensor called CWIS, one of the most successful ocean color sensors. But that's its kind of response function. That's the only light it sees in those very narrow bands. So that's what these pictures are showing, wavelength versus sort of the weighting function of the light response. So a couple more things here real quickly. The way I think about this is I mostly work on the satellite end of things, but sort of in the radiometry stuff, dabble a little bit more off and on into the IOPs. But I always try to think about this as, again, on the left panel, this is the light pathway to the satellite. So in this figure, these green lines show the ocean color coming out of the ocean, going towards the satellite. There's also a signal where the sun is, again, coming into the atmosphere. Some of that's getting scattered by the aerosols and things in the atmosphere. That's making satellite. And then there's these other cases called validation calibration. So in this spectrogram, the validation calibration, which are really the gray and yellow lines, are data we're trying to collect to actually then verify patterns in the color and make sure that that satellite is kept in really good check. The data is not drifting, that satellite sensor isn't getting worse over time, or if we do, how do we correct for it? That's way up at the end of that bubble chart I showed before. Somewhere in the middle of that bubble chart, between radiometry and IOPs, is what's on the right hand side. The radiative transfer, and there's a whole bunch of buckets in this section. It's kind of talked about. You'll see the IOPs, all the equations for the IOP, all the derivations. And then it goes to the radiative transfer equation, which sits in between there and the radiometric properties. The connection with radiative transfers, making that connection between the IOPs and the radiometric light measurements. From that, you can drive a whole bunch of other things that tell you a lot more about the ocean, or maybe it's easier to make these apparently optical properties and then go back into the radiative transfer equation using some surrogates. The other thing that's really important here too is that what I talked about, you also have to consider all these boundary. What's the sea surface? How much stuff is in the atmosphere? How much skylight is there relative to the sun? So it's a pretty complex equation, set of equations. Don't get overwhelmed. But that's where I just wanted to show you a perspective of. There's a lot of depth in each one of those bubbles going from one to another one. So last thing, this is in the presentation. You can also get it from LabSphere. I found this very useful. This is a brochure that LabSphere has. It's sort of a cheat sheet for a lot of radiometric terms and units. This is freely available. Matter of fact, I think you can order it as a laminated version if you want off the website, and they'll ship it to you. But I found this is really helpful. It does a lot of terminology, sort of the peak clear conditions that you can expect from different sections of the Earth in terms of sky illumination conditions. I'm just pointing out, it's in this presentation too, if you want to look at it, but you can go to the LabSphere and get it and download it. The other thing I liked about this is because while we just went over some terminology, more and more optical oceanographers are starting to centralize on the right units and the right terminology. But if you go way back into the history, like the last 25, 40 years, yeah, the terminology is all very different. And more importantly, the units get changed around all the time. So this is a really just handy cheat sheet. You should be able to do this anyway, but for me, it was a really good cheat sheet when I'm trying to change like 3 different units on the radiance values. It has a very good table here for you to use. And manufacturers often of instrumentation often also use all kinds of different units. And sometimes even different symbols, which is really confusing. So I think that's it. Over the next week, I hope you enjoy the set of presentations this week and next week. Enjoy those photons out there. Good question. I go into that. Yeah, that was the validation one. So I think that is. Yeah, that's like another lower aircraft image. Basically, you can think of that. Oh, it is green. You're right. Both validations.
Make the correction and send it back. All right, we're gonna take a little break because because it's the first day, we have to test, obviously, the communication, all of the different devices. So I'm gonna be connecting via a different program. So we're gonna test that real quick. You guys can take 15 minutes, get some coffee, go outside. Here comes Sunday. 2 seconds left.